quickly finish two body problems, right, chapter, and then two non-inertial reference frames. In order to save time, I sort of prepped before the class, and I usually derive all these, right? Just short derivations, but since I said I feel like we are one class short, so I decided to just glance through this. So usually after proving, that's what we did in the previous lecture, we proved Kepler's first law, right? So that orbits, elliptical orbits. And then Kepler's second law we proved in chapter 3. Now what's left? Kepler's third law. And Kepler's third law can be derived from Kepler's second law. Sounds funny. One law can be derived from the another law. But anyway, so from Kepler's law, you remember in chapter 3 we derived this, the aerial velocity, all right, equals to L, angular momentum, divided by 2 mu. Mu is the reduced mass in this case. So what do you have to do? You just need to sort of move variables around, separate them like this, right, and integrate. Right, for elliptical orbits, because that's Kepler's wrote his laws for those elliptical orbits. So if you integrate, assuming that tau is the period, let's say tau is the period, right? And so since you integrate over ellipse, so the total area of an ellipse, of course, we know, right, pi semi-major axis times some semi-minor axis, right? So if you integrate it, all right, then get rid of the constant b, because b and a can be connected, right? It's a little bit of massaging, right? Maybe like a few minutes of derivation, and you can end up with this expression, right? Which is Kepler's third law. So the square of the period is proportional to the cube of a semi-major axis, right? Okay, so now we have all three Kepler's law, right? And now also useful expression, which relates, again, usually I derive it, right? Maybe I will post my notes, right, about this to Blackboard. Expression which relates total mechanical energy of a system and eccentricity, right? Actually, if you look deeper at this expression, effectively it relates what? It relates E and L, which are basically, okay, total mechanical energy and the angular momentum. Basically, those are, E and L over here, they describe mechanical properties of a system, right? E and L, some constants which are usually determined by the initial conditions when you launch a satellite or something, right? So, but anyway, those are mechanical properties of a system. And eccentricity, it's a geometrical it describes geometrical properties. So basically, it's an equation which relates mechanical properties of a system with a geometry of the system. Again, this can be easily derived, right, so I decided to skip it. It's not that crucial. Right? It's fun, but again, as I said, not that crucial. Now, next, so let's finally finalize all the, draw all the curves of the same picture, right? So here's the sun, right? That's where the origin is, right? And if eccentricity equals 0, right, we showed it, in that case, you're going to have circular orbit, right, with the sun at the center of the circle. If your eccentricity is between 0 and 1, less than 1, then of course the object is going to have an elliptical orbit, right, with the sun being at one of the foci. So this is one focal point here. You have the second focal point of the of this ellipse, and we proved this in the previous class. And then, of course, we did not derive parabola, but it's very similar to the derivation of elliptical orbit. It's actually much simpler, right? So it can be easily done. It's like 2 lines of derivation, very simple. So parabola parabolic orbit is possible when eccentricity equals 1. Eccentricity equals 1, of course, total mechanical energy is 0. For the circular orbit and elliptical orbit, of course, total mechanical energy is negative. And hyperbola, again, deriving or proving that under these conditions, when epsilon is larger than 1, we're going to end up with hyperbola. It's very similar to the derivation of an ellipse, also as tedious, right? It would take, like, I know, again, maybe 15 minutes of derivation, so I usually never go into that, right? But anyway, it can be shown that if eccentricity is larger than 1, in that case, total mechanical energy will be positive. In that case, the trajectory is a hyperbola. Right. So pretty much that's what I usually discuss. But again, as I said, I usually go through the derivation and this derivation. This time I decided to skip it. Again, it's fun, but not that crucial. So after this, we can say enough of central forces, two-body problems. So now let's move to chapter 9. I usually spend like 2 classes discussing chapter 9, but now we have only one. That's why I complain at the very beginning. Right? And about mysteriously disappeared class somehow. So anyway, so non-inertial reference frame. So basically up to this point, every time, in all problems, in all chapters, right, in all examples, every time we used a inertial reference frame. Why? Because only in inertial reference frames we can use Newton's second law in that nice simple form. A net force acting on object with mass m leads to acceleration of that object a, right? Again, only in the inertial reference frames. So that's why we you remember the first lecture of this semester, and that's why we introduced Newton's first law in order to find and define those inertial reference frames, because we need to find them all the time. But sometimes, or actually quite often, we basically are stuck in the non-inertial reference frame. Right? For example, like we are all here on the Earth, which is spinning and also orbiting around the Sun. There are tons of accelerations, right? So strictly speaking, of course, we are in a non-inertial reference frame. Of course, with a certain accuracy of certain degree of approximation, we can say, okay, if we want to describe the motion of a car, yeah, we can still use okay, treat a non-inertial reference frame as an inertial, right? But of course, strictly speaking, we are in a non-inertial reference frame. Quite often, we cannot neglect the fact that we are on a reference frame which is, for example, spinning. Because we're going to look at the example, right? So when you, let's say, when you shoot a missile, right? It travels over with a large speed, over long distance, right, over a reasonably long period of time. As a result, if you neglect that you are in a non-inertial reference frame, you're going to get wrong results. You're going to miss targets all the time, right? But of course, if it's something simple like shooting a bullet over a short period of time, short distance, right? So we can neglect the fact that we are in a non-inertial reference frames. But sometimes you cannot neglect it, because then your description of the process are going to be quite off from real life results. Okay, so and as a result, yeah, we need to develop a procedure which can be used to describe motion of objects from the point of view of a non-inertial reference frame. So we're going to divide this process into 2 steps. First, a reference frame is going to experience only translational acceleration, right? It's very simple. And then a reference frame which spins. Right. And of course, if you have a complicated, right, yeah, you can superimpose those two results and you can describe motion of an object in a reference frame which experience translational acceleration plus spinning, right? So let's start with reference frame. You remember my abbreviation RF, reference frame, not radio frequency. Right, probably I'll use blue. All right, so let me put a big bullet. So RF, which we wrote accelerates translationally. Accelerates translationally. Basically, no rotation. No rotation. Right, okay. And we're going to use the point mass because we're going to start with Newton's second law. And again, you remember Newton's second law was written or is written for a point mass. You remember all those fundamental laws are stated for a point mass. Okay, so maybe where should I draw here? So let's assume that this is our point mass, M. And of course, it can experience some actual forces. And again, you need to realize that actual forces, again, forces which comes from an interaction, from interactions of this object with other objects. Actual forces, they don't care in which reference frame you use to describe the motion. They just act, and they don't care where you sit in an accelerating frame or stationary frame or grounded frame or spinning frame. Doesn't matter. They just act, and exactly the same force will be everywhere. All right. Okay, so let's assume that there is some force acting. Oh, maybe this way. So force F. Again, it's actual force. Maybe I should write here actual ACT, actual force. And so let's start with a inertial reference frame because we have fundamental equations written only for inertial reference frame. With a reference frame, we don't have any other options. We need to introduce first inertial reference frame, all right, and then see what can be done, right? Okay, so let's say this is our inertial, which we wrote, okay, S naught, and I will emphasize. So this is inertial RF. And so position of this mass can be defined by the position vector R small, right? But now let's introduce a non-inertial reference frame, which accelerates translationally, let's say that way. Okay, I will use probably blue color. Right, so where should I draw? Okay, probably like this. So let's say this is reference frame S, and this is non-inertial. Non-inertial RF. Okay, so now we can define position of this mass relative to this non-inertial RF using, okay, I forgot. I use subscript 0 to define position of an object relative to inertial reference frame. You see, here I have 0, and it makes sense to add subscript over here, R sub 0. But position of M relative to a non-inertial reference frame, of course, we're going to use define using R without any subscripts. And then, of course, position of the origin in a non-inertial reference frame can be defined using position vector R capital. Right? Okay, so now let's start from the foundation, Newton's second law. Right, so we know foundation, so that MR double dot, MR0 double dot equals to the net actual forces acting on the system. Okay, we know that's what Newton's second law is, right? And now, so let's try to make a transition to non-inertial. So of course we can use the triangle of these vectors, and of course we can write that r naught equals to r small plus r capital, right? Of course we can differentiate it twice, so we can plug it, and of course we will end up with mr double dot plus mr capital double dot equals to f. And now, yes, so that's what we got. It's still Newton's second law, right? But now written in terms of r small and r capital. And now we need to, before I start what I started discussing, I forgot to show that this reference frame accelerates with acceleration a that way, for example, right? So as a result, r double dot capital, it's a capital, that a, right? So now I can, let me rewrite one more time, mr double dot plus ma equals to actual force acting on the system. So now we need to sort of come up with an idea or conclusion. How should we look at this equation? I can tell you, maybe you're not aware, but most likely you are. You are deeply, okay, we are deeply in love with Newton's second law. Somewhere very, very deep, right? We use it all the time. We describe motion, right, over us, over systems, right, using Newton's second law. It's a very, very strong, deep habit. Basically, it's sort of in our blood. So as a result, even if you are in a non-inertial reference frame, you will still try to apply Newton's second law. Since we have such a strong habit, it makes sense still to present this equation in the form which resembles Newton's second law, but in a non-inertial reference frame. Right? It's sort of like as I said, we are deeply in love, and you know, when you are in love, you basically you see images of your beloved, right, almost everywhere. So let's try to create an image of Newton's second law, but now in a non-inertial reference frame. But of course, we are not supposed to fake it artificially to do something. No. What we're going to do, very simple. We're going to just move this term ma, which is, you see, on the acceleration side, m times acceleration side, and that is a force side. Move it to the force side. As a result, it would look like, resembles Newton's second law. So we will have like mr double dot acceleration in a non-inertial reference frame, mass times acceleration. And all the rest of the terms, we just move to the force side and call them forces. This term on that side, ma, again, we will start calling it a force, but it has nothing to do with the force. It's just the nature of this term is just mass times acceleration. But it's more convenient to arrange it in a way so that it would resemble Newton's second law. Move all the rest of the terms except for mass times acceleration in the given reference frame, and the rest move to the force side. All right. So that's the idea. All right. Okay. Maybe I will write. So we are in love with Newton's second law. So let's make it look like Newton's second law. So we will write mr double dot equals, again, F is a net actual force. It can be tension, gravity, right, normal force, whatever, actual forces. And now we have some additional fake force, fictitious force, right? You can insult it any way you want. But again, this has nothing to do with the force, because you remember, force was introduced to describe interactions between two objects. This force has nothing to do with that. It's just a mass times acceleration. But for us, from the point of view of an attempt to describe the process, it's more convenient to present it in this way, right? Okay, so now, and this, we can call it F fictitious, you can call it, as I said, inertial force, right? So fictitious equals to minus ma. We can call it inertial force. You know what, probably I will put in a quotes force. Right. Okay, so, and we're going to do something similar when we get to a rotating reference frame. So for examples, why it's better to write it, to write this equation in this form. Okay, you're sitting in a plane, or maybe I will draw. All right, so let me draw. So let's say this is the plane. Looks fat, all right, but you know what? It looks ugly. Right, and let's say here you are sitting, right, in a plane, in a chair. And this plane accelerates, let's say with acceleration a. And obviously you are trying to describe, for example, yourself, motion of yourself sitting in a non-inertial reference frame. So you are in non-inertial reference frame. So what are you going to experience? Let's say you don't know what is happening outside. It's just you, your chair, right, and all the windows are closed. So during the acceleration, you suddenly start feeling that a normal force will start acting on you from the chair, right? From the back of the chair, you will start feeling normal force acting on you out of the blue. Okay, whatever the nature, but it appeared. You can feel it. But at that moment, you, as a person, for example, who knows physics, you should have panic attack. Why? Because we think all the time about using Newton's second law, right? F equals ma. And now we have an actual force, normal force, acting on you forward, but you're not accelerating. F equals ma. If there is a force, only one force, there is nothing else in the horizontal direction. There is an actual force acting on you, but you're not accelerating in your reference frame. Yeah, it's deserve of a panic attack, right? So, in order to keep this person sane and still use Newton's second law, we introduce this fake force, fictitious force, which would act, which acts right in the direction opposite to the direction of acceleration, this way. So it will be ma. And now with these two forces, they balance each other out. And as a result, so net force equals 0, your acceleration is 0, and you can relax and enjoy the flight. So now you see that Newton's second law works, right? Net force equals 0. As a result, you are not accelerating in your reference frame, right? So because we all the time think in terms of Newton's second law. And when we introduce these fake forces, fictitious forces, yeah, it helps us to describe behavior of an object, still kind of using Newton's second law in a non-inertial reference frame. So another example. For example, you are in a bus. All right. And let's assume the driver pressed the brake. So, of course, acceleration will be this way, right? And so what would you experience? Of course, you will start flying, right, forward, right? No, arms should be up, right? So, right. So you'll be flying. Again, how come, right? Again, you think in terms of Newton's second law. At this moment, you feel that not a single force acts on you, right? There are no single force acting on you, but you're flying forward, you're accelerating. How come? Right? Again, we are all the time, we try to think in terms of Newton's second law. And so now if we write this equation in this form, so now we have this fictitious force pointing in the opposite direction to the direction of acceleration. So that force, ma, allows you to justify the fact that you're flying forward. Right? It's more convenient because of the strong habit of us thinking in terms of Newton's second law. Only for that reason, every time we move those mass times acceleration terms to the force side. All right. You know what? These examples. No, I'll skip because I want to get to. It's an example of a pendulum in the accelerating car, right? And of course, it will be displaced and sort of it will be at a certain angle, positioned at a certain angle, if acceleration is constant. And I used to describe that. I used to find the angle of that equilibrium position using inertial and non-inertial reference. Right? It's just a very trivial manipulations, right, of this Newton's second law in a non-inertial reference frame and inertial. All right, I will skip it. I will skip it because I want to get through rotational reference frame. Okay, so it's all obvious except for why we want to write this expression in this form. Okay, so now so the next natural step. So here we discuss reference frame which accelerates translationally, and now let's assume that we have reference frame which spins. So, okay, probably I will write, so that was the blue bullet, so let me continue with the blue bullet. Right. Rotating reference frame. Right. Now they will be quite, yeah, we'll have to get through some derivation. So again, two reference frames, one inertial, one is non-inertial, right? Probably I will use what? Blue color for, no, red, let me start with red for an inertial reference frame. So let's say this is X naught, Y naught, Z naught. So that is reference frame S naught, and it's a inertial. And then a non-inertial reference frame spinning. And their origins coincide because basically we know how to describe translational acceleration. So let's remove that from this picture. And I will probably use black, blue, a non-inertial. So let's assume that this is Z. And then maybe here somewhere X, I know, Y, right? And this blue non-inertial reference frame is spinning around this axis of rotation. Right, so this is axis of rotation and angular velocity omega. So maybe it's spinning. So this reference frame S, of course, it's a non-inertial. Right, so this non-inertial reference frame is spinning around this axis. Right, so this Z spins, this Y spins X. Right, so it's a reference frame which spins. So then, let me introduce the unit vectors. Of course, here it will be E, for example, 1. This will be E sub 2. This will be E sub 3 hat, right? And similar, we can introduce unit vectors for a inertial E sub 2, 0, E sub 1, 0, E 3, 0, and so on, right? And now let's take a completely arbitrary vector. All right, so I'm running out of color. Okay, I will probably use green. So completely arbitrary vector Q. It can be position vector, it can be velocity, it can be acceleration, it can be angular momentum, can be torque, whatever vector. It doesn't matter. Okay, so now let me write, so Q arbitrary vector. It can be, as I said, a position, velocity, acceleration, right? Angular velocity, right? I don't know, torque, anything, anything you want. What we want to get or relate, we want to relate a time derivative of this vector, time derivative, dq over dt, in the reference frame S naught, and the time derivative dq over dt in the reference frame S. So we need to relate time derivatives. Okay, let me write something. All right. Okay, let me write. So let's relate dq over dt in S naught and dq over dt in S. And you should probably, you see the reason why I'm trying to find these time derivatives, because what's our goal? We need to, again, rewrite Newton's second law, which is mr double dot equals the net force, right? So we need to, of course, we will have to find r dot. So instead of q, once we find this relation, right, we will replace q with r. So first we will write r dot, then r double dot, and then we will adjust our Newton's second law. All right. So that's the goal. Okay, so let me separate this. I think picture is more or less complete. And now let's start. Vector Q. Since origins are coincide, right? It means that vector Q in both of this reference frame, Q in S equals to Q in S naught, right? Which one I wrote first, it doesn't matter, but yeah, let me write first Q in S naught equals to Q in the reference frame S. Of course, they are not equal only if there is a sort of displacement between the origins, like in this case. As a result, we ended up with this triangle. But if origins are at the same spot, that's what we have. So Q in one reference frame equals to the Q in that reference frame S. All right? Okay, and now let's write it in terms of unit vectors and then differentiate. So, of course, I can write it as summation of I from 1 to 3 Q, which were subscript. Okay, I use just QI0. I, it's x, y, z basically, or I can use 1, 2, 3. N times e to the power of, I think I still use I0, yeah, I0 hat equals to summation, again, from 1 to 3, qi and ei hat. So in S naught and in S. And now let's differentiate d over dt, because that's what we want. And now, remember that S naught is inertial, right? So these unit vectors, 1, 0, 2, 0, 3, 0, they are true constant vectors, right? Because they're not spinning. So the time derivative of them is 0. It's like basically Cartesian coordinate system, you remember? And what is the time derivative of x hat? 0, y hat 0, right? And z hat also 0. But of course, if you look at the, for example, cylindrical coordinates, phi hat time derivative will never be 0. So, and of course, remember, right? So that dE, for example, 1, 0. Okay, let me use I0 over dt equals 0. Right? They are truly constant. Truly constant vectors. Oops. Truly constant. Yeah, basically, as I said, Cartesian coordinates. So as a result, let's differentiate it with respect to time. Again, remembering that this is 0. So as a result, we'll have summation dq I0 over dt e I0 hat equals, so the left-hand side is quite simple, and of course the right-hand side, since this reference frame is spinning, so these derivatives of these vectors are no longer 0. So summation dq I over dt e I hat plus summation qi and derivative of unit vectors. Okay, so you know what? This is obvious. What is this? It's just a derivative of q with respect to time in a inertial reference frame. Here the same derivative of q with respect to time in the non-inertial reference frame. And here, yeah, we have to look at this carefully, right? So let me write, so dE I hat over dt, and I will put a question mark. And so let's recall simple thing, like V equals to omega cross R, right? So I'm planning to use similarities in order to come up with the conclusion what is going to happen with that time derivative. So this can be written as dr over dt equals to omega cross r. Right? So then, if we divide the whole thing by 1 over r, you will get something which looks like this, right? So here we have unit vector d over dt omega cross a unit vector, right? So we can write that time derivative of a unit vector in a non-inertial over unit vector in a non-inertial reference frame with respect to t equals, but now of course instead of omega small we have omega capital. That's our angular velocity. So omega crossed with the value of unit vector itself. All right. So here we have r and r, or unit vector r hat and r hat. right? So we can plug it into in that formula, and now we can rewrite. We're almost ready to get to the right conclusion. So it's a time derivative of q with respect to time in, this is in S naught, S sub 0 equals to dq over dt in S, and plus this. You know what? Omega, it's a constant vector, right? At least there is no any subscript I. So here summation over I from 1 to 3. So I can take omega outside. So I can write omega where is it? Yeah, crossed. And here summation over I q I e I hat, right? So basically what we have in the bracket, yeah, and also this is in S, you remember? So this term, it's in S, and we differentiate it in the reference frame non-inertial. So I have to add, of course, subscript S. Okay, so now I don't think I need that, so I can erase, and we can actually write down the formula which relates these time derivatives. That's what we needed. Yeah, I will erase even the title. So, yeah, I just need to rewrite it and frame it so it will be dq over dt in the inertial reference frame equals to time derivative with respect to t in S plus. You know what? Probably I will write here. So this is obviously just q in reference frame S. But you remember we started from the fact that vector in S or S naught, they're equal. So of course I can write it in terms of S naught easily, but it's even more convenient just to drop a subscript at all. Right. So I will just write it as q, because the vector itself, any vector itself, it doesn't matter which reference frame you use to describe it. So now over there I will omit that subscript. So it will be omega crossed with q, right? So that's our formula which relates time derivatives. And now we're ready to actually start rewriting Newton's second law, because we know how we can make transformation of time derivatives. So let me check if I mention everything. Yeah, it's enough. So now finally let's rewrite Newton's second law. And we're going to make one simple assumption. It's not a big deal. So we're going to assume that angular velocity is constant. You will see just one additional term disappear. If you assume that angular velocity is not constant, then you will see when and where an additional term will appear. But since we're going to use our results for a Earth spinning, and angular velocity is constant, so that's the reason why we're going to make that assumption, right? Okay, let me put a new bullet, and so let's assume that, oh, too many lines over here. let's assume omega is constant. Example here, rotation of the Earth. Rotation of the Earth. Okay, and so now Q, it's R, right? Position vector. So as a result, we can write expression relating velocities. Right. So we're going to end up with dr over dt in S naught equals to dr over dt in S plus omega cross r. So expression relating velocities. But we need to have a second derivative in order to sort of rewrite Newton's second law. So we're going to use R not double dot. Again, not 0 means that it's an inertial reference frame. Okay, let me write. So it's a second derivative of R with respect to t in S naught. Right? So it's d over dt, of course, in S naught out of what? Out of this, right? So this is the first derivative. Now we need to differentiate one more time that. So I will write it. So it will be dr over dt in S plus omega cross r. And now we're going to recycle this formula one more time. But for which vector? For this vector. So now effectively this is our vector q. Right? As we wrote, it can be used for any vector q. Right? You can use even superposition of those vectors. Right? So that's our q, and we can apply this formula one more time, and we differentiate with respect to S naught, you see? So we just need this d over dt in S out of this vector plus omega cross this vector. You see the point? Okay. So this term, so it's a d over dt in S out of that vector. So dr over dt in S plus omega cross r. And the second, omega cross that plus omega cross dr over dt in S plus omega cross r. Oh, no. Conservation of brackets. All right, so I don't need this bracket. Yeah, now it's correct. Okay, so now let's open it up. And we're going to use also what? dr over dt is just r dot without subscript 0. So probably I will write here underneath, so dr over dt, of course, in S, let me denote it as r dot. And of course, r double dot will be the same thing. Right. So, okay, let me start from this point. So r0 double dot equals. Right. So here, r dot without 0 and another dot, r double dot. Then differentiate this term. Again, you remember omega is constant, right? Omega is constant. Basically, that's where we use the fact that omega is constant. If omega is not constant, then when you differentiate this term, you will get two terms, right? What a big deal. Now we're going to get only one term. I will emphasize so that omega is constant. So it will be plus omega cross, and again, it's a differentiation with respect to s. I mean, with respect to time, but in the s reference frame. So as a result, it's just a r dot, right? And now that one, those two terms, so it will be omega cross with r dot, again, no subscript 0, and plus omega cross omega cross r. Okay, so these two guys are exactly the same. We can combine them. Right. Right, so they give us 2 omega cross r dot. And so basically, yeah, that's how we can relate accelerations. You know what, probably I will, no, I'm not going to rewrite. I'm just thinking in terms of space all the time, space on the whiteboard. Right. Again, so you remember we want to now apply Newton's second law in the inertial reference frame, because that's the foundation. We have only one foundation, nothing else. Newton's second law in a inertial reference frame. So now, of course, let's recall Newton's second law, right? So which is mr0 double dot equals to F. Again, this F, actual forces. Actual forces. Right? So now let's plug, instead of r naught double dot, what we derived. So it will be mr double dot plus 2m omega cross r dot, right? Omega cross r dot, and plus that m omega cross omega cross r, and equals, it is equal to actual net actual force. And now, yeah, I erased the same point for, you remember, a reference frame which experienced translational acceleration. So now we're at exactly the same point where we have to make a decision how we should look at this equation. Basically, right now we haven't done any finicky things, right? So everything is logical, mathematically correct, physically correct, right? So now we need to arrange this equation in a form which would be convenient for us. Right, because again, you remember, we're deeply in love with Newton's second law. Every time we think in terms of Newton's second law in order to describe what we observe around us. It's a very, very strong habit. So as a result, again, let's rewrite it in a form which would resemble, right, our beloved Newton's second law, where effectively you should have mass times acceleration in the reference frame which you use, and all these terms which came from mass times acceleration. This is the acceleration side, and let's move them to the force side and start calling them forces, which is a complete insane idea, right? But again, it's convenient for us, so why not? Masses times acceleration, we start calling forces. It's a complete crazy stuff. Okay, so, and I will write the same again. Since we are, again, in love with Newton's second law, so let's make it, arrange it in a form so it would resemble Newton's second law. So mr double dot, of course, we will keep it on the acceleration side, and the rest will move to the right-hand side. But of course, both of these terms go there with minus. Who wants to deal with minuses, right? So of course, any psychologist will tell you, come on, change the signs. think positively, right? So let's do the same. Plus, we have cross products, and cross products can easily, we can easily hide minuses in the cross product. So this goes to that side with minus, but we can flip the order, and we will end up with plus. So probably I will first start with the actual force. Let me write actual force, F. Then plus 2m r dot cross omega, right? And again, the same story with these guys. Again, it'll go with minus, but let's flip one. We have two cross products. Let's flip one. I think we will flip that one in the. No, we will flip just omega and that cross product. Okay, it doesn't matter. Plus m and omega cross r cross omega. Right? Yeah, that's the way we're going to write it. So now, yeah, we can frame it and use it. Of course, yeah, we need to now give nice names to these fake forces, right? Karolis force, centrifugal force. Okay, I will probably write like this. So this is Karolis force. Right. So I'm not going to write separately in a separate line. And this, of course, okay, you know what? Let me put quotes like force. But of course, it's a fake, fictitious forces. They have nothing to do with force. Again, forces comes from interactions. Okay, come from interactions. So this is centrifugal, and again, all right, force. Right. Okay, so again, we haven't violated any physics law, nothing, right? So again, we use the foundation, which is Newton's second law, right? Probably I should frame it. So the foundation, and then just move the terms around, mass times acceleration. All right. Let's justify or explain on the example the presence of Karolis force, right? We all know, right? So I already mentioned. So if you shoot a missile over long range, right? Of course, it travels with fast, reasonably fast over longer distance, right? Over a reasonably long period of time. And if you don't include this Karolis force, then of course you're going to miss the target. Right? And it's very convenient to use this idea of the force. Although, let's show what happens, why the missile is going to miss the target, sort of from kinematic point of view. Just draw nice vectors, a nice diagram in order to see what actually happens, why the missile is going to miss it. Because all these forces, centrifugal, Karolis, they're so mysterious, right? Really mysterious, because they're fake. Okay, I don't need this, so I can erase it. And let's justify Karolis force. And then, if we still have time, we'll try to justify the centrifugal force. I will skip this. All right, okay. Karolis force justification. Let me write something like this. So Karolis force justification. So what's the nature actually? Probably what's the nature of this force? Okay, the Earth. So let's assume that this is the Earth. It's not the Earth. Okay, slightly better. So the axis of rotation, of course, here, right? Then I keep forgetting this is latitude and those are longitudes. Okay, so let's say this is the equator. Oh, it wasn't an equator, right? So let's say this is an equator. Okay, good enough. So equator. So in the physical situation, let's say that somewhere on this longitude, let me draw this line. On this longitude, there are some bad guys. Let's say these are this point, and let me show that these are bad guys. And so, you know what we do with bad guys, right? So we can send a missile, right? And we're going to send a missile from this point. So this is the launching position, right? So which way I wrote? Okay, let me just write starting point. Simpler. Starting point. Right. For a missile. Right. And of course, as any normal person, right, who is a street smart, right? So you just aim and shoot. So it means that you will just aim your missile straight to the north, right? Towards that guy, those guys, and press the start. So this will be velocity. Let's say also direction of initial velocity, right? So, but at the same time, we all know, so this is the axis of rotation, that the Earth is, of course, spinning with angular velocity omega constant. So all points on the equator moving tangentially. And, of course, during the launch, okay, at that moment, of course, this missile also experienced some velocity vt, tangential velocity, because of that because of the rotation, right? And, of course, when missile leaves the Earth, okay, gets disconnected. Of course, this velocity is provided by the engine, right, of the missile. But of course, it will still keep this velocity because there's no any point, any forces which would. Okay, so missile will just keep this velocity as it travels towards the target, right? So now, if you assume that delta t is the travel time. All right, travel time. Then, over that period of travel time, the missile, of course, because of this velocity, it will reach that level, right? The level of the guys, bad guys. But at the same time, it will get displaced. It will get displaced by vt times delta t. Right? So we have two displacements. One displacement in that direction towards the north, and second displacement to the east. So if you superimpose these two displacements, you will get this sort of rectangle. Basically, I'm trying to describe from the point of view, from the distant star. I'm sitting, right, and observing this cruelty, right? So, as a result, missile basically travels along this trajectory, and the explosion is going to be at that point, right? Because of that velocity and tangential velocity. So now let's look where the guys are going to be. Okay, bad guys, right? Okay, these guys over here, and of course they are closer to the axis of rotation. So this is r prime, and this is of course will be the total the radius of the Earth, right? So r prime is less than r. R prime is less than r, and of course a tangential velocity of these guys, vt prime, of course less than vt, right? So it means that over that period of time, over the travel time, these bad guys would be able to complete only this displacement, which is smaller than vt times delta t. This displacement will be a vt prime times delta t, and smaller than vt times delta t. So at the moment when the missile is going to hit the ground, giving an explosion, these guys will be some distance away from that point, right? So they're going to survive. So this, in order to explain this sort of deflection of missile from the target, Karolis force was introduced. Actually, not introduced. Yeah, it's convenient to use Karolis force to describe this additional displacement over missile relative to relative to the point where the target is, right? So that's kinematics. Just simple kinematics. Because some points are closer to the axis of rotation, their tangential velocities are smaller. Points which are farther away from the axis of rotation, their tangential velocities are larger. As a result, we can see effects like this when missile can miss the target. That's it. So then, let me check if I mention, Another example, similar to this, sort of explaining the Karolis effect, right, where Karolis force is used to describe this additional displacements. Okay, let's say you climb the high tower, in Pisa, right, and from the top you want to drop. Okay, you look down, so at the point which is right below the ball, and when you release the ball, when the ball hits the ground, it will be slightly ahead of the point which was the target, kind of. So the ball will be slightly displaced to the east. Why? Again, we can just calculate this Karolis force, and we can calculate it. But again, what's the nature? Just simple kinematics. Because when you climb the tower with the ball, you are farther away from the axis of rotation. As a result, the tangential velocity, because of the Earth rotation, tangential velocity of the ball is going to be larger, slightly larger, right, but larger, than tangential velocity of the target, of the point which is right below the ball. So when you release the ball, so this ball will maintain the tangential velocity at this point of the release. Because at the moment of release, the ball was spinning, rotating with you and with the Earth in that direction, to the east. But once you release it, there is no influence from the Earth, right? So now it just keeps that tangential velocity all the way to the ground, right? Displacing itself by the distance v tangential times the travel time, like over here. But the target, the point underneath, has a smaller tangential velocity because it's closer to the axis of rotation. So that point will be displaced over the travel time by a shorter distance. As a result, now there is a sort of mysterious, unexplainable displacement of the ball to the east relative to the point which was just below the ball. So that's the nature of Karolis force. Nothing fancy, right? Just kinematics. Okay, these accelerations, right, on the acceleration side, mass times acceleration, right? It's a pure kinematics, but for the sake of our convenience, we moved to the force side, that mass times acceleration, and started treating it as a mysterious force. But again, it has nothing to do with the force. Force is, by the way we introduced the force quantity in physics to describe interactions. These guys has nothing to do with interactions, right? Okay, so yeah, I wanted to get to this point to explain Karolis force. And now, since we still have 3 minutes, let me also sort of again justify the centrifugal force. Let's assume that Karolis force is not there, so let's just focus on centrifugal force. A satellite orbiting the Earth, around the Earth, right? And you are in the satellite, right? And let's say windows are closed, you don't know what is happening, right? And let's say you have a detector which allows you to detect actual forces like gravity, normal force, tension, actual forces, right? And so you are orbiting, and let's say you, with your detector, you detect that, okay, yeah, there is a force of gravity acting on you, right? That direction where the Earth is, right? And again, you as any normal person who thinks in terms of Newton's second law all the time, again, at that point, you should start panicking, because how come that there is an actual force acting that way, but you're not accelerating that way, right? It's just, yeah, because we are in a non-inertial reference frame, and that's why we write Newton's second law in this form. So because of that, now we have additional term, centrifugal force, acting in the direction opposite to the Earth, because yes, centrifugal force all the time acts that way, in the radial direction, radial outward, in the opposite direction to the direction of the central force, force of gravity. So now with that additional term, you have gravity that way, centrifugal force in the opposite direction. They just balance each other out, and you can feel happy and again feel sane that, yeah, Newton's second law again works, because we have this fictitious force, actual force, they balance each other out. As a result, you sit in the satellite flying, and you don't experience any acceleration relative to relative to the satellite, right? Another sort of, again, example where sort of justification why we want to keep this expression in this form. You're sitting in the car, let's say on the passenger side, and you're sort of against the door. So, and if driver goes into the curve, of course, let's assume that you don't know what is happening outside. So you're just sitting with closed eyes. And so at that moment, of course, you will start experiencing the normal force from the door, right? Normal force acts that way, pushing you for whatever reasons. And of course, again, you think in terms of Newton's second law, and of course, you should start panicking. Okay, how come that there's a normal force, actual force acting on you, but you're not accelerating in the car, right? But now we have Karolis force on that side. We introduce it, right, so that we can think in terms of Newton's second law. So now we have that Karolis centrifugal force, of course, acting in the opposite direction, all right? So we have normal force this way, centrifugal force that way. They basically balance each other out, right? And you can feel happy again and think in terms of Newton's second law. So normal force that way, I mean this way, centrifugal force that way. They balance each other out. Acceleration is 0, so everything is fine. You can be happy sitting in the car and thinking about Newton's second law, applying Newton's second law, right? Just for the sake of convenience, we write it in this way. Okay, guys, so exactly 12:15, right? So what I missed, and I'm still kind of completely confused, right? Somehow one class disappeared, right? Basically, after this, I would go and applying perturbation theory, we write the expression which can be used to describe these deflections because of the objects because of the Karolis force. So basically, we usually forget about centrifugal force because that contribution is constant, but this Karolis force, there are plenty of interesting phenomena, right? So we'd just basically try to solve this equation for R, again using perturbation theory. So we'll get some formula which can be used to find a deflection of an object if you apply certain initial conditions. If you throw the ball up, all right, on the rotating Earth, is it going to deflect to the east, west, or north, south, right? If you drop it, like we just discussed, right, or if you throw it at the angle, right? So yeah, it's a very practical example, but we missed it. Okay, anyway, so one class is missing. So let's call it a day. So it's the end of the semester.